Hello and welcome to another episode from Spiral Physics Education. We're going to be looking at particles in the atom in a little bit more detail. And we're going to be looking at the forces that keeps protons and neutrons in the nucleus, the force that keeps electrons in orbit around the nucleus. And we're also going to be looking at relative masses and relative size of the charges of all of the particles in the atom. We'll be looking at what a neutral atom is and also what a charged ion is. But usually we don't say the charged ion, we just say an ion, but that means it's charged. Let's start off then with looking at the force that attracts electrons to the nucleus. So here we have our nucleus and we've got some electrons in orbit. And back when J.J. Thomson's plum pudding model was accepted up to 1909, he discovered, actually, that J.J. Thomson discovered in 1897 that these electrons were negatively charged. And there's a picture of J.J. Thomson just so you could put a face to the name. And then what happened in 1909, not only did Rutherford tell Geiger and Marsden to start doing experiments with the nucleus, but a scientist called Robert Millikan measured the charge on an electron to be minus 1.6 times 10 to the minus 19 coulombs. And there's a picture of Millikan. And then after 1909, Rutherford published his model of the atom that had a small positively charged nucleus. So that's all of the research that had taken place up to 1911. So we knew that there were things called electrons. We not only knew that there were electrons, that we knew that they were negatively charged, and we knew that the charge on an electron was minus 1.6 times 10 to the minus 19 coulombs. And we also knew that there was a tiny but very, very heavy nucleus that was positively charged at the centre of the atom. So from that then, we concluded that electrons are attracted to the nucleus due to electrostatic attraction. And that's because opposite charges attract. So that's why the electrons stick around and are stuck in orbits around the positively charged nucleus because of electrostatic attraction. So let's have a look at the nucleus. Well, if we look at the nucleus, it's made up of protons and neutrons. And we've got positively charged protons and neutrons that are neutrally charged. They have no charge. And these two particles, all the protons and all the neutrons, they're very, very close together. They're about times 10 to the minus 15 of a meter apart, which is really, really close. And if we think about the electrostatic rules of attraction and repulsion, we've got like charges. All the red spheres there, the protons, are going to be repelling each other. And if we were to use some A-level maths and physics, we would actually work out that about 2 newtons of force is acting on each proton, or rather, each proton is going to be experiencing about 2 newtons of repulsion from a neighbouring proton. And that's about, to put it into context, the weight of 2 large apples. Now that's quite a significant force on something that's so small. And if you think about, let's say, carbon, for example, carbon has 6 protons in the nucleus. And that means that each proton in there is being repelled by 5 other protons. So you could simplistically say there's about 10 newtons of repulsion on each individual proton in a carbon nucleus. And that's massive on something that's so small. And don't forget that the size of the nucleus is about times 10 to the minus 15 of a meter. So this is really, really small. But what does that actually mean? Why is it with such a relatively large force acting on such a small particle, then if this is such a big force, acting on such a small object, why don't they fly apart? Why do they still exist collectively in this nucleus? Well, quite simply, there must be an even stronger force attracting the protons to each other, or in fact, to the neutrons. There's something that's binding these particles together to be in this nucleus. Otherwise, we wouldn't have evidence to say that there is a nucleus, which we do. And that force is simply called the strong nuclear force. And it's about 100 times stronger than the electrostatic repulsion at these short ranges that we're talking about. And in fact, the strong nuclear force causes proton-proton, proton-neutron, and neutron-neutron attraction. And that means that all the protons are attracted to protons, protons are attracted to neutrons, and neutrons attracted to neutrons due to this weird, strong nuclear force. And what that also means then is that if we do consider that carbon again, in carbon there are 12 nucleons. So a proton is repelled by 5 other protons, but that proton will be attracted to 11 other nucleons. So that strong nuclear force is extremely significant. And that means that the neutrons play a pivotal role in the existence of the nucleus, because the neutrons increase the strong nuclear force, but they don't have any impact on this electrostatic repulsion. And that's why neutrons are so important in the nucleus. So let's go on to comparing particles in the atom. So we're going to start off with the electron. We're going to say that the electron has got a mass of 1. It doesn't. It's got a mass of 9.11 times 10 to the minus 31 kilograms. But you don't need to worry about that. We're talking about relative to each other. So if the electron had a mass of 1, I'm going to say it's got a charge of minus 1. And we're going to compare everything to the electron. So if those are the numbers for the electron, then a proton is around about 2,000 times the mass of an electron. But it's got a charge of plus 1. And a neutron is around about 2,000 times the mass of an electron, and it has no charge. So there we've got our relative masses and charges. And you can see from that with all the protons and neutrons in the nucleus, even if you did have 6 electrons orbiting a carbon atom, you can see there that there are 12 nucleons in the carbon atom, and you can see there from that the mass is significantly concentrated in the nucleus, and the electrons have very little, take up very little mass of the atom. So let's have a look at the neutral atom and stay with this carbon-12 atom that we've been using as an example. And if we look at carbon-12, that means it's got 6 protons and 6 neutrons in the nucleus. And here we have an image of what that means. We've got 6 red protons and 6 white neutrons there. It also means that it has 2 electrons that fill up the first shell, or the lowest energy level. And they do that. And that there are 4 electrons that fill up the second shell, or the second lowest energy level, and that there are 6 protons and 6 electrons. Oh, I think I need to add on a few more electrons around here. Bear with me. How many have we got now? I think there's around about 6 there, although one's flashing around, but you get the idea. As there are 6 protons and 6 neutrons, and they have an equal and opposite charge, one's got minus 1, one's got plus 1, the net, or the overall charge on the atom, is 0. So a neutral atom has got 6 protons and 6 neutrons, although and also 6 electrons for the carbon-12. But importantly, neutral has got the same number of protons and the same number of electrons. So what is an ion then? Well, in an ion, if we've got this carbon-12 model that we've just been discussing. Ions are formed when electrons leave or are removed from a neutral atom. And here we're going to have an electron. It's going to gain enough energy for whatever reason to leave the atom, and there it goes. Now that means there are only 5 electrons, but what's just happened there is ionization. For some reason that electron gained enough energy from somewhere to leave the atom. That's called ionization. An ion has been formed now. And that ion now has a positive charge of +1 because 1 electron has left. So if a second electron left, there we go, there's a second electron, because it had enough energy to leave or escape for whatever reason, the ion now becomes a charged ion still, but it's got a charge of +2. So remember that ionization takes place when an electron gains enough energy to leave or escape an atom. So that's it for all the particles that are in the atom. Don't forget to subscribe to the channel. I'll see you next time on Spiral Physics Education. Goodbye.